Hi, this is lecture 19 of EP1. In this lecture, we will be discussing things related to the angular momentum. Angular momentum, as the name suggests, is a concept that's very closely linked to the regular linear momentum. Just to remind you, when things move, when objects move, they have a momentum, which is a vector quantity, and it's equal to mass times velocity. And angular momentum is basically, it plays exactly the same role as momentum plays for translations. Angular momentum plays the same role for rotations, for a rotational motion. So let's start with the definition of angular momentum. For a particle, if you have a particle, and if this particle is moving with some velocity, then the angular momentum of this particle with respect to some origin O is given by mass times the vector product of its position vector times its velocity. And we will usually denote the angular momentum by either lowercase or uppercase L. So R in here is the vector that connects your origin to where the particle is. And there is a vector product here. If you have multiple particles, so this could be particle 1, but there could be other particles moving around, so particle 2, particle 3, then to find the net angular momentum of all of the particles, what we do is we compute angular momentum of each one of them, and then we add them, we simply add them as vectors to get the net angular momentum. So before we move further, it's worth remembering a few things about how the vector product works. If you have two vectors R and V, and if you want to take their vector product, the result will also be a vector. And this vector will have, so if A times B is C, and if this is a vector product, then the length of C is the length of A times the length of B times the sine of the angle in between A and B. Or alternatively, if you have X, Y, and Z components of A and B, you could use the IJK notation, and you could multiply these vectors using the multiplication table of I, J, and K, like we did 2 days ago in lecture 18. So when you multiply two vectors, just a few things to remember and to keep in mind is that when you multiply two vectors, if they are pointing in the same direction, or if they are pointing in opposite directions, but if they are aligned, then the angle is 0 degrees in this case and 180 degrees in this case. In both cases, the sine is 0, so the vector product will be 0. And you get the most vector product when the two vectors make 90 degrees. If you have, if you're multiplying A times B, then there is a quick way of kind of guessing which way the vector product will be pointing. And this is based on the so-called right-hand rule. So basically, you look at A, you look at B, you know that C is perpendicular to both of them. And what you will do is you will rotate A towards B. So this is A, you will rotate it towards B. And then the direction of the vector C is given by the right-hand rule, which is the kind of, it's difficult to explain remotely. I encourage you to look this up in your textbook and on YouTube, but it's the direction in which your right hand moves when you make this rotation. Again, it's kind of, it sounds silly, it's difficult to explain, but in this case, the right-hand rule would tell you that C is pointing inwards into the page. Okay, so I'm now on slide number 3, and on slide number 3 at the bottom, I have a drawing of 5 particles. These particles are moving in different directions. Let's assume that they have all the same speed, and let's think about which particle will have the lowest angular momentum with respect to the origin, and which particle will have the highest angular momentum. So let's pause here, look at the figure drawing at the bottom of slide number 3, and then resume watching this. Okay, so the question was which particle has the highest angular momentum. Let me redraw here what I have on slide number 3. So I have this origin here, and there are 2 particles, particle 1 and particle 2. And then I have my origin here, and I have 3 particles, particle 3, particle 4, and particle 5. I will start with particle number 5 because that's the easiest case. So the R vector for particle number 5 is pointing in this direction. R and V are aligned with each other. So the angular momentum of particle number 5 with respect to this origin is 0. Now let's look at particles number 1 and number 2. So the angular momentum is mass times R cross V. Let's say they all have the same mass. Let's say they both have the same velocity. They both make 90-degree angles with the with the R vector, but R2 is shorter than R3. Sorry, R1. So L1 will have less magnitude than L2. L1 has particle 1 has a larger momentum, angular momentum. Now it's interesting to look at particle number 3 and particle number 4. So particle number 3 is over here. I will draw vector R that connects my origin with particle number 3. And then the angular momentum of particle number 3 will be its mass times this R times velocity. So in this case, this angle isn't 90 degrees. I have some angle theta. So the magnitude of my angular momentum 3 will be mass times the length of this vector R times the speed times the sine of angle theta. And now if you look at particle number 1, back at particle number 1 and particle number 3, and if you look at the geometry of this, you will see that R times sine of theta is kind of the y projection of R. So this is R times the sine of theta. So this length is exactly equal to this length. And from here, I conclude that even though particle 3 is farther away from the compared to particle number 1, it makes a smaller angle with respect to the r vector, and in the end, those two effects cancel out. So the angular momentum of particle 1 is equal to the angular momentum of particle 3. And if you think about particle number 2 and particle number 4, you will come to the same conclusion, that angular momentum of particle number 2 is equal to the angular momentum of particle number 4. Okay, so this was particles. For particles, it's easy. The equation is L is equal to M R cross V. Now, the question is, what happens if I have an extended object? So let's say I have this object, which is oval shaped, and this object is moving with respect to this axis counterclockwise. Now, to find the angular momentum of this object, what I would have to do is I would have to divide this object into smaller parts, like so. And for each part, I would have to, now each part is small enough so that I can treat it as a particle. And for each one of them, I would have to take its mass, the distance from the origin, and the velocity. I would have to compute, let's say this particle is particle I would have to compute its angular momentum, and then I would have to do it for all the small particles, and I would have to sum it up. And as you can guess, this is basically the same as taking some sort of integral over angular momenta of small parts of this object. Now, in the most general case, when you have a complicated shape that rotates around an arbitrary axis, well, this could get pretty complicated. To do this properly, we would need techniques of tensor algebra. But fortunately, for simple cases that we will consider, where you have a simple shape and the axis of rotation goes through the center of mass, for those cases, all of this works out to a pretty simple formula. The formula is that the angular momentum is the moment of inertia times angular speed omega. So this is the magnitude of the angular momentum. And to find the direction of angular momentum vector, we will again use the right-hand rule, quote-unquote right-hand rule. And in this case, right-hand rule is used in the following way. If your object is rotating this way, counterclockwise, then you imagine holding your right hand so that the fingers wrap around in the direction of rotation. And if you do that, then the direction of your thumb shows you which way the angular momentum is pointing. So in this case, if this disk was rotating counterclockwise, by applying the right-hand rule, I would conclude that the angular momentum is pointing from the page, outwards from the page. So these things are kind of difficult to explain remotely. Again, I encourage you to look this up in your textbook or on YouTube. You could also join our help room Zoom sessions on Wednesday at 12:30 and Friday at 12:30. So now let's think about what happens to the angular momentum as things move around. And as you can guess, we will have some sort of conservation law here at some point. So you probably remember that when you have a regular momentum, then this momentum of a particle doesn't change unless there is some force acting on it. And when the force is acting on an object, then momentum changes, and the rate of change of momentum is equal to the force. We have a similar situation when it comes to the angular momentum. So if something is rotating, then the angular momentum is not going to change unless you have some sort of external torque. And when you have an external torque, then the rate of change of momentum is equal to the torque. So this is the law that describes how angular momentum changes, and it tells us that to change the angular momentum, we need external torques. So a good example of this, kind of slightly not very intuitive example of this is a gyroscope. There is this demo that we like to show our students, where you have a bicycle wheel, and this bicycle wheel is initially suspended from a rope. So let's say there is this rope that hangs from the ceiling. And since there is gravity, since there is this force mg, if you just hang this wheel like this horizontally, what will happen, of course, is that it will fall. Okay. But something interesting happens when you spin this wheel. So if you spin it really, really fast and then release it, it's not going to fall. And instead of falling, it will actually start rotating around horizontally around this rope. In my lecture slides, I have a link. Follow that link. It will lead you to a YouTube video that shows this demo. And this is kind of counterintuitive at first, because you would expect gravity to make this thing fall, but it doesn't. And to understand what's happening here, what we need to do is we need to look at the torque and at the angular momentum and see how what's happening here is related to this equation. So first, let's start with the angular momentum. I have a wheel. This wheel is rotating counterclockwise. So I will use my right hand rule. This is my right hand, fingers in the direction of rotation. And then the thumb will tell me that the direction of my angular momentum is pointing, like this to the left. So this is my angular momentum. Now let's think about the torque. What's my torque? I have this force here, the force of gravity. So this is my force. And this is where the force is applied. So this is my R. And just to remind you, the formula for the torque is that the torque is R cross F. Now let's see which way my torque points. This is my R. Let me use a different color. This is my R. And this is my F. So again, I will use my right hand rule. I will rotate my R towards F. And when I rotate my R towards F, this is my right hand. My thumb will show me that the force in this case is outwards from the page. So this is the momentum, angular momentum, and torque is outwards. And since the change in angular momentum is driven by torque, the L has to rotate and point slightly outwards from the page. And so the direction of the torque, if you think about it, will always be perpendicular to the direction of the angular momentum, and that torque will always compel my angular momentum to rotate, and that's what's causing this circular motion. So this is the first half of lecture 19. In the second half, we will get back to the angular momentum, and we will talk about the conservation of angular momentum and how it can be used to solve physics problems.